I see. Clay, do you want to share again? Are you all set, Clay?
Sure.
Okay, so let me record. So I want to welcome everyone to this week's Western Hemisphere Colloquium on Geometry and Physics. Please feel free to use the chat if you have questions, or raise your hand or interrupt judiciously. And we'll also have a question period at the end of the lecture. So I'm pleased to introduce Clay Cordova from the University of Chicago, who will talk about non-invertible duality defects.
Okay, thanks very much. Please interrupt me as you see fit. It's hard for me to monitor the raised hands, so just dive in. The work I'll tell you about today is in collaboration with this group of authors up here. And there is also a complementary paper by Omori, Katie, and Zhang that I encourage you to check out as well. Okay, so let's dive in. The modern approach to symmetry in quantum field theory is via topological operators. So we're used to now thinking about higher form symmetries, and we will indicate this in this talk by G upper Q, where Q here tells us the form degree of the symmetry. So Q equals 0 is an ordinary symmetry. Q equals 1, a one form symmetry, etc. And given a theory with this symmetry, we have some topological operators defining the symmetry, which we'll denote by UG of M. So here, G is some element of, little g is some element of big G. It's a particular symmetry group, a symmetry element action. And this D is our space-time dimension. And this notation is supposed to indicate that we're placing this topological operator that we have because we have a symmetry on this submanifold of dimension D minus Q minus 1. Okay, so with that notational orgy aside, symmetry in quantum field theory is really about topological operators. And there's an important story here about their fusion algebra. And the fusion algebra for ordinary symmetries is group-like. What that means is that if you take UG1 and you collide it with UG2, this is equal to UG1, G2. So here I've suppressed the fact that they're all three supposed to be on the same submanifold. So the picture is I have G1 and here's G2, and I bring them together, and this composite defect is the defect associated to the product G1, G2. So this fusion algebra of these topological symmetry operators is what encodes the fact that the usual symmetries are a group. So sometimes this kind of fusion algebra is called invertible, because in particular, it means that every symmetry element has an inverse. Now, of course, if you have studied topological field theory, you know that the fusion of topological operators can be more general. So in general, we could have something like UI, UJ, I and J are some abstract indices here, is some sum over other topological operators, UK. Now, what could be in the sum? So first of all, it could have more than one term. That should already be contrasted with this simple fusion algebra up here, where the fusion of G1 and G2 gave us a unique composite object, G1, G2. And the second thing that can happen, which we'll also see an example of today, is we could have defects of different dimensions here. So this fusion algebra, whatever kind of structure it is, can mix up all the topological operators of various different dimensions. And we'll see how that can work practically speaking. So this kind of more general fusion algebra is sometimes called non-invertible, to contrast it with the invertible case that I described above. Okay, so we are not the first people to think about this kind of mathematical structure. There are some prominent examples. Let me run through them. So one prominent example are Verlinde lines. These are topological lines in rational CFTs. So, for example, one thing that we'll build on today is the so-called Ising fusion category. So the Ising fusion category is built from 3 lines. There is a line which is the identity. There is a line eta, and 1 and eta together you can think of as generating the Z2 zero form symmetry of the Ising model. And then there is a more interesting line, sigma, which comes from the fact that there is Kramers-Wannier duality. And we'll discuss that a little bit later. And what is the fusion of these? Well, eta times eta is 1. That's because eta and 1 generate this Z2 symmetry. Sigma times eta equals eta times sigma is sigma. So far, this part of the fusion algebra looks invertible. But the real interesting equation is that sigma times sigma is 1 plus eta. So that's an example of this kind of non-invertible fusion algebra, which is well studied. Let me give you another prominent example. Another prominent example are anions, or generally lines, in 3D TQFTs. Here I'm thinking of unitary modular tensor categories. And you could think that these are some kind of version of non-invertible one-form symmetry. After all, the one-form symmetry are the subset of the lines in the 3D TQFT that have the abelian fusion algebra. So here, you could think that the more general lines are just some non-invertible version of that. So those are some prominent examples. And what I would like to
ask a quick clarifying question?
Yeah.
You suppressed the MD minus Q minus 1 in this discussion. In the case of the Verlinde lines, I think there's only one choice for that. It's a circle, right?
Yeah.
And that's the way I interpret
Yes.
that bit of your thing. In higher dimensional things, of course, there are many more choices. I assume that's going to play a role at some point.
Yes. Yeah. I mean, you know, when you have these objects on various manifolds, you know, what the sum is over could depend on the manifold. What the nature of the coefficients are might depend on the manifold. So we'll have to keep track of that. Indeed, right now I'm just suppressing it because it hasn't come up yet, but we'll have to be careful about it later. More questions?
Well, it seems to me that your two examples are actually the same example, right? They're closely related.
They're closely related. That's true.
But not the same.
Yeah. Okay. All right, it's great to have a co-author in the audience. It's like having someone on your team. Okay, so let's keep going. So what am I going to do? In this talk, I'm going to construct some non-invertible defect. We'll call this a duality defect. We'll give it sometimes the name D. And we'll focus on 3+1 dimensions. Though there's an analog of the construction that works in general D. And these non-invertible duality defects, they will generalize Kramers-Wannier duality. So what we'd like to do is we're going to construct these defects. We're going to explain how to compute their fusion. And we'll give a couple examples. And if there's time, maybe I'll say one or two dynamical consequences, but I doubt there will be time. Okay, so that's the plan. Questions about this motivational part? Okay. So let's proceed with the defect construction. So we'll begin with some QFT, some theory, we'll call it tau. And this is a theory with some symmetry GQ. Now, here I'll take GQ, for most of the talk, we'll imagine that GQ is actually a Zn higher form symmetry. This is just for simplicity. There are versions with more general G. And the main input in our construction is going to be a duality. So given this theory with GQ symmetry, we could try to imagine another theory where we have gauged this symmetry. By that, I mean we've coupled our initial theory to dynamical GQ gauge fields and summed over those gauge fields. And in general, this theory, T and T mod G, are different theories, but we will assume that there is a duality. So we will assume this. So this is our input in the construction will be a duality. So for now, I'll take this as a given, and we'll see that we could use it to construct something interesting. So a little comment. So note that gauging GQ implies that there is a new, so here I'm going to be, in this case, new dual symmetry. What's the form degree of that symmetry? It's D minus Q minus 2.
May I interrupt?
Yes.
You might have some choices in various terms depending on the new gauge field only.
Absolutely. Yes, absolutely. So I will try to say that more precisely. So there are indeed choices for how to make these fields dynamical, and we will, for simplicity, tune those to 0. But for each choice, you might imagine that you could get different kinds of duality defects, which could in general even obey different fusion algebras and things like that. So
there is in general no natural choice. Another way of saying it is that if you specify the emergent dual symmetry, then yes, you've specified what you have done. But the way you phrased it, I don't think it's meaningful in general.
well, to say a little bit more explicitly, I'm imagining that I know this theory and its exact coupling to background fields. And then when I say this is an equality, I mean I get it. I get an equality including the coupling to the new dual background fields.
So let me make sure I understand the issue here. I think Nadia is saying that you could couple in a TQFT for the GQ gauge field before you make it and then make it dynamical. Is that the issue?
Actually, I would phrase it differently. Only for you and Dan, the gauge field before you made it dynamical was classical, so you can add an invertible theory of the algebra.
Okay. Yeah. Okay.
So
If I've been a condensed matter physicist, I would say you tensor or a SPT.
yeah, so Nadi, I didn't specify that in the language here, but we are keeping track of that. So when I say I have a QFT with this symmetry, what I mean is I know it coupled to background GQ gauge fields exactly, including terms that depend only on these on these fields. And then I want this duality to hold, including the coupling to the new background dual symmetry. So I am keeping track of those counter terms. And that is important in that, they will show up at places.
So now I can ask the other question. If there is a duality, does the original theory tau also have G D minus Q minus 2?
Well, those symmetries get identified in the duality. So the model you should have in mind is like the Ising model at the critical point.
No, in examples, I know what you're doing.
Okay.
You're trying to phrase it here more generally.
Yes.
So for example, should we identify GQ with G D minus Q minus 2?
Yes. Yes.
But that's possible only when Q is
yeah, indeed. That's what this node is about to say. So when we gauge this this GQ symmetry then this GQ symmetry is eliminated, but we get a new dual symmetry, and we want them to be the same because we want this this duality to hold. That's part of my input. So therefore, in particular, I need the form degrees to hold.
I see. Thank you.
So this is only possible if Q is equal to d minus 2 over 2, which is of course an integer, since q is an integer. So this is going to restrict the kind of constructions that I'll be able to do with this simple set of rules. So I could do q equals 0 in d equals 2, or q equals 1 in d equals 4, etc. So I'll review this case. This is the case that will be related to the Ising model, for instance. And this is the main novelty, is the focus on that case. Okay, more questions. Okay. So we're going to build this object from a Dirichlet interface. So we will cut spacetime into two pieces. So this we'll call the left side. This is the right side. This is where we're going to build the defect D. It will be along some manifold M, which is a codimension 1 manifold. So on the left, we'll have the initial theory. And on the right, we'll have the theory where we have gauged this symmetry. So what will be the action for this configuration? So I'll have an integral over the left side of whatever was going on for the theory that I started with, plus an integral over the right side of this theory coupled to, these are the gauge fields for GQ. So these are going to be dynamical GQ gauge fields. And so here, Nadi, I am assuming that I know this Lagrangian, including its full coupling to these background gauge fields. And then, of course, you're right that I could have added potentially some SPT that's a function of AQ plus 1, some invertible theory. And this I will tune to 0 for simplicity. So I could have added something additional to what is known here, but I do not do it. Okay, so AQ plus 1 are the dynamical GQ gauge fields. And along this interface locus, which is some manifold M, I put Dirichlet boundary conditions for AQ plus 1. So that means that AQ plus 1 restricted to M is set to be 0. For the additional fields, it's just transparent. The fields on the left are identified with those on the right, as they should be. Okay, so this is a topological interface. It's a topological interface because the Dirichlet interface is topological. Another way to say it is that the gauge field is flat. Now, in general, if we did not assume this self-duality between T and T mod G, then this would just be some kind of interface between two different quantum field theories. The duality assumption that we added which was that this theory is the same as this theory, this duality assumption, this means that this object that I'm defining is an interface in a fixed theory.
Clay, what identifies the two global symmetries on the left and the right at the interface?
Yeah, thank you. In general, I will need to pick an isomorphism. So if let's be in this simple context where G is, well, in general, the dual symmetry is isomorphic as a group. So its form degree is what I said, but it's isomorphic to a group as Hom of the original group to U1. So the Pontryagin dual group.
Sorry, I guess what I mean is you have sort of double the global symmetry at the interface. So you have both. You can restrict topological defects from the right and from the left.
Yes, and those will obey some interesting things will happen to them there. Yeah.
But in order for this to be a duality interface, you might have wanted to break that to the diagonal.
Well, I don't think it is broken to the diagonal. I think they're both present there.
Oh, okay. This is different from, say, like S-duality interfaces that folks talked about some time ago, and other duality interfaces where like you would want them to have.
No, sorry, they are identical. Sorry. I mean, the Dirichlet, well, I'm about to write it, but the Dirichlet condition means that the symmetry defects can, from each side, can end on the wall and get absorbed by the wall. So I think that does do the identification that you have in mind.
Thanks. Okay, yeah, I can sort of believe that. Thank you. So yeah, never mind.
And maybe a different way of asking Tudor's question is, say I coupled the global symmetries on each side to non-dynamical background gauge fields. Will I use the same set of non-dynamical background gauge fields throughout the picture, or do I have different sets on either side of the wall?
I think you would use the same set. It's a little bit of a tricky question, though, because this defect will have some interesting fusion algebra with those things. So, but I think you would use the same set. Okay, so let me actually begin specifying that fusion algebra because it is closely related to these questions. Okay, so let's look at the region R for a minute. In R, this dual symmetry comes from what kind of operators? Well, they look like some generalized Wilson surface type operators. So I'll write them as eta of S, which is the integral over S of this dynamical gauge field. And the Dirichlet condition tells us that since AQ plus 1 along this defect is 0, we have this absorption rule, which is that eta times D is D times eta is equal to D. So that's one part of the fusion algebra. So D here is the name for this defect, and its locus is M. Okay, so that part of the fusion algebra is easy. But a more interesting part of the fusion is what happens when we collide D and D bar. So what will be the picture of colliding D and D bar? So let's try to draw it. So here's a manifold. The cross section, I'm imagining locally that the space-time looks like M times R. This cross section is M here. M is the locus on which we placed this defect. So here's D, and here is D bar. D bar is just D with the opposite orientation. And there's in between D and D bar is a region where we are gauging this. Let me now restrict to the Zn case, just to be very concrete. So if we want to study the fusion algebra of D and D bar, we have to understand what happens when we gauge this Zn higher form symmetry in a slab with Dirichlet boundary conditions at either end of this slab. And we'd like to understand what happens when we think of the slab as being very thin. And of course, there are the other dynamical fields in this problem. And we're imagining that we're first integrating out the dynamical ZNQ gauge fields. And then later we'll do the functional integral over whatever T fields there were. Okay, so let me explain how to think about this. So let's be in 1 plus 1D. So let's say that D times D bar.
Clay,
Yes.
at this point, you could have posed this problem without assuming that T is isomorphic to T mod GQ.
That's correct. Yes, yes, that's correct.
Okay,
And-
so you
and,
haven't used that self-duality yet.
Yes, yes. I mean, then we'll get an interesting algebra of interfaces between different theories. And that is still an interesting algebra. The interesting thing about, well, it's nice if you have an interface in the same theory, because then it's very analogous to a symmetry and you can maybe derive some dynamical consequences. But at this level, you're absolutely right. Okay, so let's go back to the 1 plus 1D case. So we're looking at the fusion of D and D bar. Now let's imagine that this fusion contains the identity. So here, in this case, in 1 plus 1D, that means M is a circle. So this picture is literally accurate. And let's imagine that the fusion of D and D bar contains the identity line with some unknown coefficient. We're going to try to fix that coefficient. But before doing that, we can notice that from this fusion algebra, once we know that the identity is there, we will actually know that the full algebra must look like this. Because once you see that the identity is there, you can just fuse one of these D's with eta. That's again D, but now you'll have eta appearing there with the same coefficient X. Okay, now, so what's going on? Let's try to understand this formula. So we have D times D bar gauge theory in this thin slab. And we have, we have D times D bar, and we have therefore this Zn zero form gauge theory in this thin slab. And we've seen that we now see that this fusion algebra is some number times a sum over these etas here, eta to various powers. And remember that eta is just, in this case, the integral over S1 of this one form dynamical gauge field. So this sum here is the expected sum over Wilson lines. In gauge theory that we would get when we compute this Zn zero form gauge theory partition function. So we've got the right form of the answer. And from
So-
that, yeah,
Like, can't there be defects that are in the kernel of multiplication by eta, which could be on the right-hand side?
yes, thank you. So, indeed, this is more like a way of motivating the answer. But if you wanted to be more rigorous, you could just change the logic a little bit and say that the definition of D of this fusion D times D bar is to do the partition, is to compute the path integral of Zn zero form gauge theory with Dirichlet boundary conditions on each side, together with whatever operator insertions there have to be. That's the definition of the D times D bar composite. And so from that, I'm saying that if you do that, then you would directly just get this sum right here. So this was more like a way of motivating this formula, but more logically, you might proceed that way. Then you can be convinced that there's no gap. Okay, so so indeed, continuing with this partition function logic, this coefficient x, what is that? It comes from the normalization of this gauge theory in the slab of the Zn zero form partition function. In this slab geometry. And I say partition function here, but I mean that in the generalized sense, where we have all possible other operators inserted to the left and to the right here. So we're just isolating a piece that we're computing right now. So what is x? Well, it's 1 over h0 of, okay, s1 times interval relative to the boundary of S1 times interval. It's a relative cohomology calculation because we have these Dirichlet boundary conditions, and we just need the order of this group. And this is 1. So this is relative cohomology because of Dirichlet boundary conditions. Okay, so this kind of fusion out. So to summarize, what did we get? We got that we have in this Zn0 case where we gauged it. We had zero form symmetry lines eta to the I equals 0 to n minus 1, obeying a standard Zn fusion algebra. And then we had this duality-like object, which obeyed this nice equation. A sum over group elements. Of course, the special case for n is 2 is exactly this Ising fusion category that I talked about before. And in general, this kind of structure, I believe, is called a Tambara-Yamagami. Fusion category. There's more data in that fusion category. For instance, there's crossing rules and things like that that I haven't specified. That would require a more close analysis than what I'm doing right now. Now, I'd like to highlight a key property of this defect D, which lets you a little more clearly see why it is not a standard symmetry. So again, we have the left and the right side. It's divided in two by this duality defect D. And here we have a Zn charged operator And D is topological, so I can move it to the left and ask what happens when it crosses this Zn charged local operator. And it becomes this picture here. So this is now an eta line attached. And this is now a non-local operator. By that I mean it's a operator that has a topological line attached to it. So that's of course different than a standard symmetry. A standard symmetry would map local operators to local operators. This is not doing that. So that's one hallmark of this non-invertibility in this example. Okay, so that's all I wanted to say about 1 plus 1D. The situation in 3 plus 1D is quite analogous. In this case, instead of a 0-form symmetry, we'll be interested in gauging a 1-form symmetry. And again, we will try to compute D times D bar by gauging in a slab with Dirichlet boundary conditions. Now the slab is just generally of the form M times I, where this M is some 3 manifold.
Can I ask a question?
Yep.
So the reason that eta line is attached on the right side is because it's now a twisted sector operator in this description on the right side.
Yes, I mean the right side is the left side where you have gauged this Zn.
Right.
So the operators that were charged are now are no longer local operators after gauging.
Right. And is there a way to see that this line should necessarily be ending on the duality defect?
Well, should be, I mean, when you pull it through, that's what you end up with, right? I mean, it's ending there sort of by construction. I mean, perhaps the question is more like, why can it end? And it can end there precisely because of the Dirichlet boundary condition.
Okay.
Clay, does that picture depend on the D being an isomorphism of the two theories, or does it hold in general?
That does not depend on D being an isomorphism.
Thanks.
Like you could do Kramers-Wannier duality away from the critical point, and this would still be true.
So one more question is that in all of this, we are assuming G to be finite. Is that correct?
That's correct. Gauging is a much more complicated operation if G is continuous.
Thank you.
Okay, so we're going to gauge, what are we gauging? We're gauging now this symmetry, this Zn 1-form symmetry in a slab of this shape to try to compute the fusion D times D bar. So we're supposed to sum over gauge fields. What are the gauge fields we're supposed to sum over? Well, these are cohomology classes of degree 2. It's a 1-form symmetry, so the form degree for the gauge field is 2. And they're relative cohomology classes. Again, relative to this boundary, again with coefficients in Zn. And provided everything is nice and orientable and so forth, I can identify this with h lowered 2 of m Zn. So what this means is we're again getting a sum over symmetry defects. So D let's put it on, I'll note the manifold that it's on explicitly now. D times D bar, both on M, is some unknown coefficient, which we'll have to figure out, times a sum over objects here. These are the non-trivial gauge fields. So S in H lowered 2 of M Zn. And now the Wilson surface, eta of S. So these, I recall you, are the Zn1 symmetry defects. Okay, X, again, comes from the normalization of the partition function. So it would now be a ratio of cohomology classes because we have discrete gauge theory, discrete higher form gauge theory. So we need the ratio of this to H1 of the same stuff. And this is nicely 1 over n, or more generally 1 over the order of the group, independent of what M is. That's a nice fact that holds. So Jacques asked me before, how do things depend on the manifold that everything is on? We can see that if we summarize the fusion algebra. So we have D times M is eta equals eta times D of M is D of M. And then we also have D of M times D bar of M is 1 over n sum over S in H2 of M Zn eta of S. So you see here some dependence on the manifold that things are on.
So
Just
Clay,
yes.
I have to ask, you've been asked this before, but I'm gonna ask it again.
Okay.
I still don't know the answer. I still don't understand the answer.
Okay.
So D of M, we could interpret D of M, you know, in fully local field theory, defects are associated with objects in some kind of extended category, higher category.
Yeah.
Right. So D of M, maybe we should think of as an endofunctor of the category of line defects. Similarly for D bar of M.
Did you say category of line defects?
I did. We're doing the 4-dimensional case. Yeah,
Okay.
I would say that. So on the other hand, well, that's a way of interpreting it that I learned from Dan.
Okay.
And on the other hand, I don't really understand how eta of S, this 2-dimensional object, could be considered as an endofunctor of the category of line defects. Or put more crudely, D and D bar are objects in some extended category, maybe a 1 category, and eta of S is in
Well, this is, I mean,
category, or maybe we could take the Poincaré dual picture. But in any case, they don't match up. So I don't understand this.
well, no, this is a codimension 1 object here. This is what might be called a condensation of 1-form symmetries, where I have taken the 1-form.
S is 2-dimensional in a 4-dimension space. How is the sum of eta of S?
I'm summing over it in M, right? So this is like gauging the 1-form symmetry on the submanifold M. So if I have a theory with a 1-form symmetry, I can try to define a codimension 1 defect by gauging that 1-form symmetry just along M, some codimension 1 manifold. That's what's happening here.
How does eta of S act on line defects?
It acts as a 1-form symmetry. It acts by braiding. Eta of S is a 1-form symmetry. It acts naturally on line defects.
Let's see, line defects in the 4-dimensional bulk.
Yeah.
if S links the line defect, right?
But no, but sorry, if I choose a general line defect, these are particular, well, they're homology classes. Usually when we want to act on a line defect, we would take the linking sphere. That's exactly what I don't understand. If I want to act on a line defect.
Is your question how a one-form symmetry acts on a line defect?
Well, yes, I think the rule is that I take the linking sphere. And then I take the, I insert my higher current on that linking sphere, integrate it. And that's how it acts on a line defect. Now here you have a sum over homology classes. If I give you a line defect, some line defect, how is that acting on the line defect? Is it
Each one of them,
one if S, I mean,
it's the phase that is their charge if they're linked for each cycle S. So I'm not sure why it's any different than having one of them. If you know how one of them acts, you know how some of them act.
I know how a linking sphere acts.
Do you understand how to compute how eta of S for a particular S acts on a line?
No,
Well, you just need to ask if S links with the line. And then, you know, every time you cross to move them far away, you may need to cross some number of times. And each time you cross, you get a phase that is the charge of the one-form symmetry acting on the line. The exponentiated charge.
Your line is disjoint from M necessarily? Is that true, Clay?
Yeah. And then
Yeah,
we want
You have
to
a surface,
I'm
so you
not
have a
sure what
surface in M, and the question is how well does it link the curve, Greg?
I'm not sure one would call that an action. You're defining an endomorphism of the line with this sort of linking procedure.
well,
So eta of S would give you an endomorphism of any line. It sounds like that's what you'd get if you pass the line through this d times d bar.
yeah, but since it's a one-form symmetry, it's invertible. Yeah, it's just some phase acting on the line. It's some phase multiplying the line.
so we've got lines off of the, let's see, M is what? The total
M is
space?
a three-man, no, M is a
M is a
three-manifold.
manifold. Okay, so if the line defect is not on M and the
Mhm.
surface is in H2 is in M,
Yeah,
I'm not understanding this linking.
It could be linked, it could be unlinked. It depends on the relative positions of the surface and the line, but they're both.
they're the right dimension to measure that. They're the right dimension configuration to measure that. Yeah.
Well, maybe we should pick this up at the end. But Clay, can I have you repeat, how do we interpret the right-hand side as codimension one defect? Can you just repeat that?
Well, I would interpret it as follows. I would say that in general, there's a general class of constructions that people call condensation, which is a way given some defect, how to construct a new defect. Let me say the simplest example, and I think this is one of the simpler examples of this. We don't need to be too fancy. So I would say that if you have a symmetry in quantum field theory, you know, if some obstructions vanish, you can gauge that symmetry. Let's talk about discrete symmetry here. You can gauge that symmetry and get a new quantum field theory. Okay, but there's something else you can do, which is that you can gauge that symmetry just along a submanifold. So pick a submanifold inside your ambient spacetime and gauge, in this case, Zn one-form symmetry just along that submanifold. So couple your theory to dynamical degrees of freedom that live just on M in this construction and sum over them. And I would say that's a way of defining a new codimension one defect. It's a little bit of a cheap codimension one defect because it is built from these lower dimensional defects, but it's codimension one nonetheless. So that's how I would think about the right-hand side here.
All right, thanks. Think about that.
Okay, so there's this key property which again, we should write. So if here is our defect D on M, and here is some Zn1 charged loop, then if we move D past this, we'll keep D here. But now, instead of a loop, we have an eta surface attached. So this is one way that D differs from a standard symmetry. If we try to move it past a charged line operator or loop, it becomes a loop with a topological surface attached. Okay, so that is how I think about this general construction. And now I'd like to give you at least one example and make a list of some other examples that are known. So the example I work with is U1 Maxwell theory. Okay, so this theory is defined by tau, and for tau is not the same as the theory tau. It's the electromagnetic coupling, which is 4 pi I over g squared plus theta over 2 pi. And it has some higher form symmetry, which will be relevant to us. It has an electric one form symmetry, and it has a magnetic one form symmetry. And we are going to look at gauging a Zn one form subgroup of the electric symmetry. So what happens when we do that? At the level of Lagrangian, this is very easy to do. You have the dynamical gauge field A, and wherever you see A, you just replace it by A over N. So here, this is a connection on the dynamical U1 for the dynamical U1 gauge group, and here I'm doing this as a connection for U1 mod Zn, which I'm then identifying with U1. So figuring out what happens when you gauge this one form symmetry is very easy because of that. And in particular, because the whole action is quadratic, we can easily see what happens to the coupling when we do that. So when we do this construction, tau changes to tau over n squared. Okay, so if you just gauge the Zn one form symmetry, in general, you make a topological interface between a theory with coupling tau and a theory with coupling tau over n squared. If I want to make an object like what I was discussing above, I'll need to combine with some kind of electromagnetic duality to see if this tau over n squared is ever secretly equivalent to tau. So let's use electromagnetic duality. So electromagnetic duality says that tau is equivalent as a quantum field theory to A tau plus B over C tau plus D, with A, B, C, and D integers, and AD minus BC equals 1. And so I could try to use, for instance, S duality to see if tau over n squared is ever the same as, is ever S dual to tau, which would mean that it's minus 1 over tau. So if I wanted to combine this gauging with S duality to get an interface in the same theory, I would need to solve an equation that minus 1 over tau is equal to tau over n squared. And you can do this provided that tau is tuned. So we'll take tau equals in, which of course means that the theta angle is 0 and g squared is 4 pi over n. So if tau is tuned like that, then so at this special tau, we have a duality defect. And this duality defect is a defect in the same theory. That's its nice property. We could even write a Lagrangian generalizing some construction of Gaiotto and Witten. So let's try to write the Lagrangian. Okay, so what should we put here? N over 4 pi. The left and the right region will be defined by saying that some coordinate x is less than or greater than 0. So in the left region, we have the standard kinetic term. In the right region, the same, with different fields. And along the locus x equals 0, I will put a Chern-Simons term, a mixed Chern-Simons term, coupling the two sides. Why do I write this? So why should we have this mixed Chern-Simons term here on this wall? I should say that this is generalizing Gaiotto and Witten. Who discussed the case n is 1. So what's the equation of motion? On the wall, it's that dA left equals minus I star dA right, which is equal here. This is electromagnetic duality at tau equals in. This would be equal to 1 over n dA right dual. And this is the identification I was trying to achieve by combining S duality and the Zn gauging. So that's the motivation for this Chern-Simons term. Okay, so that's a nice free class of examples where we can write explicitly the kind of defect that we're talking about. Okay, I guess I'm basically out of time, so I'll just enumerate some further examples and hint at some interesting things you can do. So some further examples. It's early days of this, so so not many things have been worked out explicitly yet, but there are some interesting continuum examples. So you could look at SO8 pure Yang-Mills. They're also version with matter, and this has interesting duality defects for this slightly different group than the kind that I was talking about before. You could look at, of course, SUN n equals 4 super Yang-Mills at tau equals I. Well, at this special locus, SUN is, of course, super Yang-Mills is identified with SUN modulo Zn gauge theory with the same symmetry. And this is the result of gauging a one-form symmetry. That's how the gauging of the one-form symmetry modifies the gauge group. It's electric one-form symmetry. So n equals 4 super Yang-Mills at the self-dual point has a duality defect. Maybe I'll mention one other. This is not due to me. This one is due to Omori, Katie, and Zhang. They discussed PSUN, pure Yang-Mills, non-supersymmetric at theta equals pi. This has a duality defect. And they use that to inform some results about the dynamics of that theory, which before this were a bit mysterious, at least to me. So finally, there are also some lattice examples, but I guess I'm basically over time. So I didn't have any time to
Can you
say.
just elaborate on the last point? What did they say about this theory at theta equals pi?
Yeah, I can elaborate on that point. So, if you go back to SUN Yang-Mills at theta equals pi, of course, there is in general, if you're even n or at odd n, there's some other similar structure. There's something like an anomaly, which tells you that at theta equals pi for SUN Yang-Mills, the theory cannot be trivially gapped. Now, if you gauge the one-form symmetry to go to PSUN, something funny is happening, because on the one hand, the gauging isn't doing much to the dynamics. So that conclusion should still hold, that at theta equals pi, there's something non-trivial there at long distances. On the other hand, there is not even any obvious symmetry to discuss at theta equals pi for PSUN, because you've broken the time reversal symmetry, for instance. So what they showed is that this non-trivial topological field theory that is the most likely candidate for living at this special value of theta for PSUN Yang-Mills, that this has the neat property of having this duality defect. So if you like, that's kind of like a symmetry. That's what like replaces time reversal symmetry in telling you that the dynamics are non-trivial.
Are you saying that at theta equals pi, PSUN at theta equals pi is another Z2 symmetry?
It's not a Z2 symmetry.
Is Z2 non-symmetry?
Yes.
But then what's the new fact about the dynamics that we didn't know before? You give a better explanation, but of a phenomenon that we knew. But is there really a new phenomenon here that was not known before?
I would say that not if you knew, if you take as a given that you know what the dynamics are in SUN Yang-Mills at theta equals pi. Or
Yeah,
that
I
you
don't
know,
think anybody disputes that statement.
Yeah. So indeed, so once you know that, then of course you know that those dynamics will not be affected by gauging the one form by going to PSUN.
Okay.
So if you like, what their analysis is something like a symmetry-based reasoning directly in this theory that tells you that there has to be something non-trivial.
Maybe before we continue the discussion, we should thank Clay for a very interesting talk. So if you have a question, you can raise your hand. I think Andy Knightsky, go ahead. Oh, no, you don't have one. Sorry, Greg, go ahead.
Okay, well, I'm a little hesitant to ask this question because I think everybody except me understands this. But could we go back to your picture with the line defect going through the this Hanani-Witten type picture? Yes, picture there, right, the key property, yes, good. Okay, I think that's defining operationally what you mean by eta of S. But I for one, do not understand the following. If I have a general closed one manifold in a four manifold, and I have a surface in a sub three manifold, I don't know what you mean by the linking number. And so I don't know, it's not so obvious to me what is the quote standard action of the one form symmetry on the line defect. However, if we assume that the three manifold is deformable so that we can put that loop inside the orientable normal bundle neighborhood of the three manifold, then we could talk about pulling it through. If we can pull it through, then at the moment it goes into the three manifold, the linking number in general position is defined. And so the thing I have on the right-hand side looks three-dimensional to me, and then my objection disappears. But I just want to point out that it's not, I don't think it makes sense on general lines. At least I don't understand how it does. I need to make some assumptions. I need to assume the normal bundle is orientable. I need to assume that L can be pushed into a small neighborhood of the zero section of the normal bundle. And then I think the picture could make some sense. And I think this picture that you have here is operationally what you really mean in terms of defects.
Okay, that's fair. I have to process a little bit the issues that you're raising, but let me think about them a little bit. I don't have anything crisp to say right now.
All of his pictures had M cross I, so the normal bundle wasn't just orientable, it was trivial.
Yeah, I mean,
I was, okay, I was being more generous, but maybe he requires a trivial. I mean, well.
Well, I'm just saying what the pictures were.
One, I mean, you know, there are not too many real line bundles.
I am not, yeah, so I mean, I'm not interested in a non-orientable situation right now. So the ambient space is orientable, M is orientable, and as a consequence, the normal bundle is trivial.
Okay, Nati?
Yes, I'm puzzled. I tried to get some help from Shuheng on the side, but I'm still puzzled. You make a very strong restriction that the theory has a self-duality, but a lot of what you say, I think would go just as well if after the gauging, it's not dual to the original one.
That's true.
And
yes.
we have worked out, you and I and many others, lots of examples like that. So
That's true.
how much of what you say is applicable in the more general setup?
The fusion algebra and these key properties are applicable in the general setup. The part, and I should have perhaps organized my talk better to get to the parts that are not applicable in the general, that I don't think are applicable in the general setup. The part that is not applicable, I believe, in the general setup is that if this is an interface in the same theory from one theory to itself, then it can constrain the dynamics in a fixed theory. So for instance, there can be things analogous to anomalies for this kind of object. So the existence of this kind of object can sometimes obstruct a theory flowing to a trivially gapped phase. That is something that I do not know how to think about if it's just an interface between two different theories.
I see. I think in other words, you say that when it is the same theory, you can put it sideways, and then it is an operator acting on the
exactly.
space.
Yes, exactly. Yeah.
But
I didn't discuss that, so you might you rightfully complain. I get it.
Okay, any
But
other?
it seems like this is not, this should be generalized more generally. So we should be thinking, and I'm glad Dan is here, we should think about the theory more generally with all its variants. I shouldn't reuse this phrase these days, but with all its slight modifications, such that this thing can be put sideways.
That's true. Okay, so I mean, I don't really know. You want to know
Because you don't really
formalism?
use the fact that there's a Hilbert space and operators acting on the Hilbert space, et cetera, et cetera. You don't use all that. You have a more Euclidean picture.
Well, we did in the paper, just not in this talk.
I'm sorry, I can't keep up with all your papers.
But it will be put to use in when discussing the dynamical consequences, the Hilbert space interpretation and all that.
No, I understand it for the Hilbert space interpretation. For the constraints on the dynamics, you might need more. But for most of these properties, I don't think you need
These
them.
fusion algebra properties, I think you're right. I do not need more.
Yeah, right. Yeah.
Sorry to beat a dead horse, but let me make my point in a slightly different way. You have loops; those are one manifolds. You have M as a three manifold. In general, one manifolds and three manifolds intersect in a general four manifold. What would you do? What would you say if they intersect transversally?
Well, they won't intersect S typically. That's what you need to ask about this question.
Well, that's not quite true because S is a homology class, so you can move it around, and presumably you can slide it around M until it meets the intersection point.
Yeah, and the rules about that's true that I could move them so that they do meet if I wish, and the rules about one form symmetry acting on lines tell you exactly what phase you're supposed to adjust the correlation functions by when they cross. So the rule of a one form symmetry defect acting on a line is exactly supposed to tell you what cost you pay when you cross the surface S across said line.
But then if you have two different representatives of the same homology class, which differ by crossing the line,
Exactly.
how do I tell what eta of S means, right? I mean, how do I know if I have number one as opposed to number two, which one is on which side and what the phase is for which one? I agree that maybe you can tell how it changes, but I'm having a hard time with the formulation in terms of a homology class.
But when there are lines inserted, we have to cut our space a hole where the line is inserted, and that creates some new homology classes.
Well, then how do you apply the operator which was defined in terms of old homology classes on the new homology classes?
This formula is what you're supposed to insert if nothing else intersects M. That's how an OPE is generally interpreted in QFT. Right?
Okay.
You have operators away from the colliding locus, and you want a replacement rule where the only things in the picture are this. That's what I have in mind here.
Okay, I like that.
All right, well, maybe this is a good point to thank Clay again. And to say that the next talk will not be until January 24th. It will be Hiroshi Oguri. So to wish everyone a happy and safe holidays. And we can continue informally if you want to stick around. Thanks.
And Clay, if you could save this notebook as a PDF and send it to me for posting on the web, I would appreciate it.
Oh, sure. Yeah.
That was a great talk, Clay.
Thanks, Nadi.
I'm happy that maybe the third or fourth time I hear it, I understand better.
Me too. I appreciate all the questions and the interest.
Hey, can I ask you again about what you said about gauging on a submanifold? So supposing I take just an ordinary finite group G that acts as a symmetry.
Yeah, I would
think
say
you might use the word zero form.
Yeah, for zero form symmetry. I would say that